and welcome. We'll just welcome to Kopernik's Friday Night Live, a live stream. Pardon me. My name is Drew Desker. I'm director of the Kopernik Observatory, and it's great to see all of you who braved the weather to come out here. We'll do a real quick pan. So there's Mr. Roy Williams, who will be our presenter this evening, and we have a number of people here who came up. A lot of people did our family STEM hour earlier. And we've got a number of people already already on the live stream. In fact, when Linda said the salt truck already went by her house. So glad to have a live stream tonight. So my guess is there are a bunch of people who would have come up otherwise. Anyway, it's great to have you here. Definitely some familiar faces, but some new faces here. By show of hands, who's here for the first time? All right, so a number of people, and who here are members? All right, a good mix there. All right, so for those that are here for the first time and not members, the people who are members are actually have a very special knowledge. The Kopernik membership is actually quite a valuable thing to have, especially if you like places like Kopernik. Kopernik belongs to an association called the ASTC, Association of Science and Technology Centers. It's a group of consortium of over 350 other science centers that share reciprocal membership. So for $60, you can get a family membership here, and then you could take it to Roberson, you could take it to the Museum of Science and Technology, most up in Syracuse. You could take it to the Intrepid down in New York City, or the Franklin Institute. You just went down to the Intrepid? Isn't that a neat place? It actually has the Enterprise, which is a space shuttle that actually didn't fly in space, but it was actually used as a demonstration for testing landing. And but anyway, so if you like this kind of place, a Kopernik membership is a great thing. It's also, being around the holidays, it actually makes a great gift as well, and there's no supply chain issues with that. So I'm going to switch over here to our website for those people that are watching. Again, we welcome those watching here. Jennifer, Jumai is actually watching from Maryland. Also, so those on the on the live stream, if you're just type in where you're watching from. We'd just like to share that with everyone. And Jennifer is watching for the first time, so it's great to have you with us as well. On our website, we actually, as website should be, it's pretty informative. Tonight we talk about our black holes on Black Friday, and tonight was the last of our Friday night family STEM hour, where they all built the hovercrafts. So you're going to take your hovercrafts home and check them out and do some more experiments at home. Great, excellent. And also this month and next month we are actually supporting Chow. So if you brought, if you come up for an additional program later in December, bring some food up, put it in our food bucket barrel there, and we'll give you complimentary tickets to come back for a future program. And of course, next Tuesday is Giving Tuesday, and we are participating in that. And again, Kopernik is a nonprofit. We're not associated with any university or any government agency, so we really depend on memberships and Friday night programs like this, but also donations to help keep the doors open. So if you're in a position to help us out on Giving Tuesday, that'd be really helpful. Really appreciate that. We'll give you a couple of things that are coming up down the road. So the next couple of weeks, we've got sort of two different events, one that's going to run twice. So next Friday, on December 3rd, and also we'll repeat it on December 17th, we run a program called The Star of Bethlehem. It's a movie that actually is a gentleman who was an attorney, but he was interested in astronomy, and he wanted to know what did the wise men see back around the time of the birth of Christ. And so he used some software to sort of dial back to that time and talks about what he found. It's actually quite interesting. And so again, we'll run it on the 3rd and the 17th. And starting in December, our programs will start at 7 p.m. But then the following week, on December 10th, Phil Cooper, who has done a number of programs here, and if you've been here back around the time when we were doing our sort of celebration of the moon landing, Phil is an extraordinary model builder, and he brought his Saturn V models up, as well as the command module and lunar module. He's now actually building models for Cornell for their astronomy department. He's that good. So he actually has built 3 different new models, one of the Saturn V, but also the Falcon Heavy, and also the SLS. And so he'll bring those models here on the 10th and talk about what we're going to be doing with those rockets. And Phil is just he does his homework. He does extraordinary work. So come on up on either of those Fridays, or again, if you can't make it up, the program on the 10th, the Titans to the Stars, will be live streamed. Because of copyright restrictions, we cannot live stream the Star of Bethlehem movie. And then finally, on December 18th, which is a Saturday, we put our order in for some clear skies, and but we're going to do a sort of holiday horizons up here, an event for the family to come up, and we'll do some experiments and some demonstrations, and then hopefully our telescopes will be open. We did something similar for Halloween, which was very, very, very successful. So, all right, Theodore is watching from Missouri. We have Jennifer in Marathon, and so anyway, it's great to have you on the live stream. So, one of the things that we do here again at Kopernik is our Friday night programs, and we're not necessarily going to try to turn everybody into an engineer or a scientist, but we want, or at least become, hopefully, just stir some curiosity in you. And again, I see a bunch of smaller younger people here, and I'll tell a little story. One of the programs we do here at Kopernik is called Girl Power, and it's a program where we're really trying to promote more women in STEM. So a few years ago, we had this Girl Power. We always do a subject. We always have a female subject matter expert either come in and do a presentation or do a video conference with us and talk about the work that she does. And so a few years ago, we had an astrophysicist from NASA, the Goddard Space Flight Center, talk about the work that she does with using satellites to look at carbon dioxide levels and what it's doing to the planet. So then after the presentation, the girls get to ask her questions. And this one girl asked the question, how did you get interested in astrophysics? And she says, well, it's an interesting story, because when I was in college, I was an English major. My boyfriend was a physics major. And we would go from observatory to observatory. I eventually dumped the boyfriend, but I kept the astronomy. And so you never know. And now she has her PhD in astrophysics. So you never know where a seed's going to get planted. And so that's really sort of what these Friday night programs are about, is planting seeds and maybe stirring up some curiosity. So tonight's program is about black holes. And how many years have we been doing this, Roy?
I think 10 years.
10 years now. Roy Williams on our Kopernik staff always does this program, Black Holes on Black Friday. And so over the 10 years, things have changed. We've actually got some pictures of black holes now, and so we're going to turn this over to Roy and let him.
All right, great. Thank you. Thanks. Thanks, Drew. All right. Okay. All right. Awesome. Thank you. Well, good evening, everybody. Welcome to Kopernik Observatory. So I thought we'd do a little pre-show as people are still kind of strolling in, and show you what's out in the night sky. So if it was clear tonight, this is what we'd get to see. The whole time? Okay.
All right. So
Okay.
Let's try that.
Test live stream. Can you hear me live stream?
Yep.
Type in, if someone could type in.
Yep.
You're good? Okay. All right. Sorry. We're just going through the sky, those on live stream, what's out in the sky this time of year. So anyway, let's bring it a little bit later here. So kind of like a little twilight there, so you get to kind of see the idea of the sun setting and stuff. There we go. So what you got here is Jupiter. You got a line of planets going on right now. You got Venus, you got Saturn, and then you got Jupiter, and then even Uranus is right here. So we're starting to get this line of planets. So that's one of the exciting things that's happening right now in the sky. Down here, you can click a button and see what constellations they are. Here comes Taurus, one of my favorite constellations, the Bull. And let's fast forward a little bit, because a very interesting object is right there called, you got the Orion, the constellation Orion, and then you got something called the Orion Nebula. Okay, so we're going to be showing you some pictures of nebulas in a moment. And so here's the Orion Nebula. So this is one of the main objects we get to see in our telescopes during the wintertime. Late fall, early winter is the Orion Nebula. So come back up. Drew listed all those shows that we got going on and special events going on in the winter. So, all right. So let's get going on today's program. Black holes. So yeah, like Drew said, we've been doing this for a number of years. And all right, so we're good? Okay. Presentation. So many buttons to push. And then what do? I do it with the clicker?
You can do it with the clicker.
Okay. All right. Great. And anyway, yeah, black holes, ghosts of our universe. All right. So the reason why we call them ghosts is because they're very difficult to detect. And when I was in high school, it was really a theoretical object if they even existed at all. All right, type of thing. So in order to talk about black holes, we got to talk about how stars form, because black holes come from stars. Here is part of the Eagle Nebula, and it's a summer object. And this is a snapshot of just part of what we call the pillars of creation, if you've seen that famous NASA picture. And if you look closely, there's these little peninsulas, these little things jotting out here. And over here, would you do it? Yeah, there we go. So right here, these little pillars jotting out. And at the top of those pillars, it's kind of glowing. That's where new stars are being formed. They're being formed in these globules, they call them. And, we'll talk about how stars form, but they're quite beautiful. And they're giving out, right when they form, they give out a lot of ultraviolet light, which causes the gas in that nebula to glow. And that's why we can really see it so well. So anyway, the classic diagram here on top shows you life cycles of the stars. This is going to we're going to see this diagram a couple times. I got it in the slideshow a couple times because we're going to keep talking about it. But what we got here on the bottom picture is what we call a protoplanetary disk, or a star forming. And what you got is, by gravity, you got contraction of gas and dust that's collapsing downward and eventually forming a star in the center of that solar system. So this is how our sun formed. This is how all the stars formed. So inside the nebula I just showed you, in those little peninsulas, this is what you got going. And the Hubble Space Telescope, using aimed it at Orion's Nebula, and got to see these up close, these protoplanetary disks. So we do know they exist. So once a star turns on, we're talking about temperatures in the core of about 15 million degrees. All right, and at that temperature, electrons are stripped off of their atoms and creating what we call plasma. Now, plasma is not the blood, right? This is a different plasma. Plasma is gas that can conduct electricity. So there's plasma closer to you than you may think. In fact, it's over your head right now. So the fluorescent lights, we send electricity through it, and it glows, and that produces a plasma. Okay, and you've ever seen those night light, or those lights with the lightning? Forgot what they call those, but that's also plasma too. So you're kind of familiar with what plasma is, and that's what stars are made out of. So it's gas that's been so energized that it can conduct electricity. Now, releasing a great deal of energy through what we call nuclear fusion. So in the center of that core at 15 million degrees, we got something called nuclear fusion forming. So there's a kind of a balance going on. There's the outward pressure of the gas, and then inward, so you got nuclear explosions going on, basically, forcing the gas outward, but then you got the pull of gravity forcing it inward. So it's kind of a balance game going on. All right. So what we got going on here is, I'm looking for my picture to pop up. I thought I had a picture. Nope. Let me go back. So when is a star? A star, a forming star is considered to be a true star when nuclear fusion takes place. Basically, we're taking hydrogen and forming it into helium, and it loses a little bit of mass. So 4 hydrogens are turning into 1 helium. You lose a little bit of mass, and that energy, that mass is converted into energy. Einstein's famous equation, E equals mc squared, is demonstrating the idea of the conversion of matter into energy, and that's what's going on inside stars. So a variety of stars, they come in different sizes and colors. Blue to red, yellow, orange, things like that. There's no green. Well, maybe there is, but we can't see it. The human eye doesn't see, low light levels can't really see green. Surface temperature, it's all related to surface temperature. So it's opposite of your bathtub. You might think, red stars would be hot, but really it's the blue stars that are the hottest, and the red stars are the coolest stars. The more mass you have, the brighter and the hotter stars get, so they tend to be more bluish, okay, with the more mass. And this is the other irony, is that they don't last as long. So you would think if you had more mass, it would burn longer, but it doesn't work that way. It actually goes through the nuclear reactions even faster, like that. So yeah, so more mass equals actually a shorter lifespan. So what we got here is a diagram showing what I just talked about, nuclear fusion, the different layers of the sun. And you can see up here at Kopernik in the daytime, we have different solar filters to use. When we're projecting the sun with our heliostat telescope that's next door in our physics lab, we get a big 9-foot disk of the sun, and it was very spectacular to see the eclipse on that. But that shows us our photosphere, which is where the sunspots are, and then where you got the prominences, these prominences right here, these flares coming up, so to speak. That's the hydrogen gas being emitted from the sun, and you're looking at what we call the chromosphere. And then finally, the other layer to talk about is the corona, which means crown, ring, crown, and that's the outer atmosphere of the sun. So those are the kind of the different layers of the sun. And there's that nuclear fusion I talked about. You got 2 different isotopes of hydrogen coming together. Deuterium is one type of hydrogen. Tritium is the other type of hydrogen. They come together. It releases a neutron, and it forms a helium. And so basically what you get out of this is that stars are making helium in the beginning. They make helium. And then later on, helium combines to make other elements. And so we're made of stardust. That's really what Carl Sagan talked about. So there are engines of building the periodic table. They build all the way up to iron, and then iron is the most stable element. And then when the star explodes, it releases the other elements. So, any questions from online? No. Okay. How many we got online? 17. Okay, 17. Good number. Okay. Let's see. 4. So here's the classic HR diagram, Hertzsprung-Russell diagram, and it shows you the temperature on the bottom versus how bright it is. And you see different versions of this. It looks like this is based on the sun. That's what I like. So the brightness of the sun is a 1. These stars are 10 times brighter, 100 times brighter, 1,000 times brighter, and then maybe, I don't know, up to nearly 1,000,000 times brighter than the sun. So it's easy to rank it to the sun. That's the star we know the best, right? And then the ones below this number down here are dimmer than the sun, much dimmer. Oh yeah, I got to do over here. I'm sorry. So people at home didn't see that. So, or nobody saw it. Okay. So anyway, so let me do that again. So up here is these are the real bright stars. Here's the sun right here. So right there is one solar brightness, one solar luminosity, and then the ones down here are dimmer, and the ones up here are brighter. So now, what's this diagonal line? This diagonal line is what we call the main sequence, and that's where stars live their life. They live 90% of their life is lived on that main sequence. So our sun is currently right here. It's a G, what we call a G star. So this is the spectral class OBAFG. So we're right here, and so that would be our sun. So we basically started as a solar nebula over here on the chart, became a yellow star where we are now for billions of years. Eventually, we're going to turn into a giant, and then we're going to shed the outer layers of our atmosphere, and what's left over will become something called a white dwarf. We'll be over here. We'll be very dim and but hot, yeah, dim but hot. But anyway, let's see. So just to give you an idea of size here, what we got here in terms of size, the Earth compared to the Sun, and then maybe a red giant, just kind of give you the size that we're talking about. Now, what happens when we have different size objects? What happens is Einstein came up with the idea of space-time. And the idea is that there's this fabric of space that gravity is warping, and space-time is being warped. And so it looks something like this. And if you were in our lobby earlier, you got to see our what we call spandex universe. And we got a little one up here we're going to show in just a second. And then you can see that the bigger the object here, it's going to pull down the fabric. So space-time, as mentioned by Einstein, is the never-ending fabric of the universe. The fabric bends around objects due to the object's gravity. So Isaac Newton thought of gravity as being like, you know, a rope between two objects. You can pull on it, right? They pull on each other, which works fine. His formula for gravity works fine. But Einstein is more precise. So it explains, for example, why Mercury's orbit is kind of messed up, and it kind of travels around the sun. It precesses around the sun in a weird way that Newton's laws didn't really describe. So anyway, let me just show you the big thing that we were able to do with this in the beginning of the 20th century in 1917. Some scientists, some astronomers were able to prove Einstein's theory. So, you know, Einstein had this theory of relativity, but the evidence is very difficult with the equipment they had at the time to prove some of this stuff. So what Einstein said was that the sun should actually warp space around it, and there are stars behind the sun. So during an eclipse, when the sun when the moon is blocking the sun, we won't get that glare. We should see stars that shouldn't show up on our star maps because they're behind the sun. They shouldn't really be there. Okay, and this kind of shows that. So you have, well, I got to do it over here. Okay, you have starlight right here. So this is what it, how should I explain? This is the way it looks like to us. So here's the Earth. Okay, the star looks like it's over here, but in reality, it's over to the left. It's behind the sun. So the gravity is warping. So who told you that the shortest distance is a straight line? That's not always the case. So anyway, so according to Einstein, it can be curved. Okay, the shortest distance between 2 points. So anyway, that's the idea. So let me do a quick demonstration of that. We might need, we're going to need light. So we got our spandex universe here, and we're going to just kind of demo how this works. All right, good job on the lights. Okay, so we'll swing the camera over. And so we got our little version of spandex universe. So, all right, there we go. Okay, so what we got here is the fabric of space and time. We have a star in the center, which is warping space and time, and we're going to let our planets go around just like this. So we got a bigger one in the lobby. So yeah, there they go, and they do hit sometimes. Yeah. So this is how it works. Now let me just show you that experiment. I got carried away here. That wasn't what I was supposed to show you. It's mesmerizing. It's just like the kids get on this and they just want to. Like I have this in my classroom, and they just get on it. Something calms them down. I think it mesmerizes, hypnotizes them. So here's what we got. We have. Are you on?
Yeah,
okay.
Here we go. But after time, if they launch those marbles a little too fast, we end up finding marbles like months later all over.
Yes, that's right. That's right. So we don't want to lose our marbles. So what we got here is, so let's say my hand right here, this star, this is starlight, and it's going to the sun is going to deflect it. Maybe the Earth is over here, all right? And let's see if I do this right. And it deflects it. There we go. I got it. So you see how that deflected it? So that's what they were able to see. The funny story about this, maybe a year or two before, there was an eclipse. And those same scientists tried to view it, but it was during World War I, and the Germans stopped them. They thought they were spies or something. So there's some funny story along those lines. But a year and a half later or something, they were able to see a similar eclipse. But anyway, that gives you an idea that, now let's see the real evidence here. And my next slide kind of shows the real evidence, there we go, okay. All right, there we go, good teamwork. Nope. So that's what there's on. There we go, okay. So this next picture shows that evidence. Oh, it was in 1919. So it was 1917 they tried the first time, and they almost got held up by the Germans. So anyway, so kind of proving Einstein's theory in that famous eclipse. So I don't know if you can see it, but there's two little stars right here. I mean, off by very small amounts. It was really right at the edge of what they could do and prove at the time. All right. So we do know that the more massive a body is, the more it pulls on this space and time situation. So if you're looking at it in terms of, like, here's your normal star, or what I just did, we could pretend that's a normal size star. We call this a gravity well because it looks like a well going downward. And then there's something called a neutron star. This is even more dense, more heavier, more gravity, and it's pulling down. All right. And then finally, we get to something called a singularity, which is what a black hole is. So it goes so far down, it's almost as one single point of matter in extreme density, okay, extreme gravity. So that would be your black hole. So you're just talking about, different amounts of mass giving you different amounts of gravity, which warps space and time deeper and deeper into that gravity well. So let's just look at the life cycle of a star. All stars begin in a stellar nebula, and then they go on to that main sequence that I talked about. 90% of their life they're hanging out. Everything's hunky-dory. They're producing hydrogens turning into helium, and then they start producing the other elements, and they start dying. So it turn into a red giant. And this is going to happen to our sun. Our sun's going to about 4 billion years from now, it's going to swell out. It's going to swallow up Mercury. It's going to swallow up Venus. It's going to get close to the Earth. We don't know. We're going to turn into Mercury. Our atmosphere will be gone. And then what it does, it puffs its outer layers away and creates something called a planetary nebula. And here's a planetary nebula right here in the diagram. Oh, planetary nebula right here. And then in the center of that planetary nebula, you have a white dwarf, which is, I showed you on the chart, it's very dim, but very hot, okay? And then it cools off. I guess they call it a black dwarf, okay? So that's one life cycle of a small star. Our sun is kind of like on the dwarf side. And then if you have more of a massive star, it follows a similar sequence. But what happens, it will, instead of puffing away to this planetary nebula, it supernovas. It creates a violent explosion, and it will either turn into what's called a neutron star, which is it's this really dense material. Like if you had it's just all neutrons really close together. If you have a spoonful of it, they say it would weigh as much as a battleship. So that shows you how that we're weird. The matter that we exist, our matter, our atoms are normal in the sense that there's so much empty space in them. But in this stuff, it's really weird stuff. I don't think the spoon would be strong enough, or the person. But anyway, that's what they say. But finally, you have a black hole, even more massive star, where it's so strong that not even at some point when you get too close to it, not even light can escape. And that's why we call it a black hole, because light is going to get sucked into it, so you can't observe it. So you're wondering, if we can't observe light from it, then how do we know it's there? we'll talk about that. But that's basically the sequence there. Any questions on life cycles of stars? So
where is the point where they break off the planets?
Where they break off the planets? Where's the point? Okay. Yeah, well, planets are gonna start having problems when a star. So the question was about planets. When do the planets break off, so to speak? So they're gonna start getting swallowed up, and I'm sure that's gonna push them out. Yeah, that's a good point. And just speaking of planets, as we mess around with those marbles, and you see sometimes marbles get flown out because they get too close to another marble. That happened early on in our solar system. We know that there's planets that were tossed out of our solar system because they got too close to Jupiter or some of the other planets. In fact, even Mercury can, if it has close approaches constantly with Venus, it could theoretically get thrown out. I mean, but they're thinking that that could be 1 billion years from now, so it's not something we'd see. It's not something we'd see. So anyway, that's a good question. All right, so I'll keep that over here. And then, okay, so black holes. So they're intense gravitational field when a star totally collapses. That's how I would look at it. It has to be much larger than our sun. I didn't give you any numbers, but I'm hearing like 10 times the mass of the sun, even bigger. I think 10's the smallest you can be in toward being a black hole. So much larger mass than our sun has. We talked about the star's life cycle. Gravity becomes so big that it compresses, forming a black hole. Okay, so yeah, we already did this, so we're good there. So yeah, we talked about how stars are in this delicate balance of nuclear explosions, pressure outward versus the gravity, and most of the time it's very stable. All right, and then what happens is that we start running out of the explosions, so to speak, and so we start running. What happens is that the pressure starts winning over versus the gravity, and it just swells up. So it's equalized for a long period of time, but then eventually the gravity starts losing between those two forces. And there's that. So anyway, planetary nebulas are beautiful objects. Now you might be thinking, why do they call them planetary nebulas? What's going on here? When a red giant sheds its outer layers, it leaves that white dwarf. In the old days, in the 1700s, people's telescopes, astronomers' telescopes, weren't that good, and these things look like round discs. So if you see a planetary nebula, we can show you the ring nebula, which I got, which is not sure if that's the ring, but it looks like that. It could be a different picture of the ring that I don't recognize. But anyway, the ring nebula is a classic object that we watch all the time, and it looks like a donut. Okay. So, but a lot of them do look like little planets, okay? In fact, there's one called the Ghost of Jupiter. So that name kind of stuck. It's kind of a terrible name because people think it's planets. But here's some more planet nebula. Like, in the National Enquirer, they call this the Eye of God or something. This is the Ant Nebula, I think. So they come up with all these names. Here's the ring, okay? So they come up with all different types of. So the core of the star that all that remains after planetary nebula is shed, and the core is still very hot, but it's about the size of the Earth. So this star is dense, and it's about the size of the Earth, and it's extremely hot. But because it has such a small surface area, even though it's hot, it should be bright, right? But because it's so small, it's dim because it just doesn't have enough surface area. Okay, so white dwarfs form a star that has less than 8 solar masses. Yeah. So anyway, so now what happens when we get a bigger star? So we're going to be in this bottom row here. So it's the mass that determines what's going to happen to the star, and we get, if we're a really big star, it will turn into a black hole. Now, how can we spot them? What's going on here? This artist's conception of it is kind of showing what's going on, how we can spot them. So when I was in high school, in the 80s, let's say, black holes were theoretical. Okay, they said, Einstein says they should exist, but we've never really observed a black hole, and it was even debatable. In the mid 60s, they had evidence of some black holes, some what we call X-ray sources. Cygnus X1 is an X-ray source in Cygnus, and that was a #1 candidate of a black hole. Okay, so what's happening here is that typically we have material falling into a black hole from another star that's nearby, that's in orbit, and it's creating this jet of material. not only do you get this bright accretion disk, just like the marbles, right? When you roll the marbles all at once, they bang into each other. So that's going to provide heat, and that we can pick up. And then we also have X-rays shooting out at the poles of these stars because of a strong magnetic field that's causing that. So it is emitting those X-rays, and that's why we were looking for X-ray sources. Because X-rays are absorbed by our magnetic field in the atmosphere, it's hard to do X-ray astronomy from Earth, from the surface of the Earth. So we have to go launch rockets up and be in space to get above that. So anyway, so here's what it kind of looks like. You have a black hole devouring a star. So you got a companion star that's actually in orbit, and it could be in a stable orbit, okay? And it's getting its gases stolen from it. It's going into that accretion disk and really lighting up where the black hole is, okay? So now some people have thought of the idea that there's smaller black holes, right? And maybe they can interfere in our lives, right? So like socks, I always missing my socks. They go into the dryer, and no matter where, I mean, I'm missing socks all the time. And anybody, raise your hand if you have a problem with that. Missing socks. See? Now, where do they go is the question. Like, they're missing. Well, I have a theory about this. I think they turn into these things, okay? Because you have extras of these. So that's got to be it, right? So, right? You always have the lids, right? So that's my theory. So if that turns true, we'll see. Yeah, so you can have. So this is what we call direct evidence or indirect evidence, because we don't really see the black hole, but we see X-rays popping out, or observation of that. So yeah, so when a black hole devours a star, it emits radiation that can be detected by X-ray telescopes. All right, and that's pretty much it. Let me just show you. So there are some neat things to talk about, though, when black holes form, and let's kind of compare it to some other situations and kind of crank up the gravity and see what happens. So let's say if you're standing on a star, which wouldn't be a good idea, but burning up. Well, yeah, burning up. I gotta keep doing that. Okay, so burning up. So here we are. As the mass increases, so does the gravitational pull. So let's say you're on a star here, and you can toss up a ball, and it's going to come back down to you, right? So as the gravity gets stronger and stronger, you're going to not be able to toss that ball up, right? So it becomes so strong that if you even had a flashlight, that it would pull the light into itself like this, okay? So, but there is a region around a black hole that you can deal with, and then there's a line you cross. It's called the event horizon. That once you cross that line, you can't escape. So this sucker, he's on the black hole. He's doomed. So I don't know if your flashlight would work, anyways. But that's the idea. That's kind of a thought experiment. Oh, this is probably better. So here's a star. So light emits from a star, no problem. A neutron star, the light's going to be warped, okay? And then a more massive neutron star, maybe more. And then finally a black hole. Anything trying to be emitted from it is just going to loop around. Gravity is going to pull that light back. Now, let me see. So where are these black holes? I think that's what I'm going to talk about next. So here's our galaxy. Okay, we got our sun right here. We're about halfway, maybe 2/3 of the way out from the center. All right, we're in what's called the Orion arm of the Milky Way. And we believe we are a barred spiral galaxy, which means it looks like it has a little bar structure running through it. And this center of the galaxy is where there's a supermassive black hole. Okay, so now some gentleman asked me before the show, how many black holes are there? And I got to do more research in the Milky Way. But they're saying like hundreds of millions, or 100 million, which I find hard to believe. But whatever, well, I'll do more research on that. But we do know there's a massive one in the center of the galaxy. And let me see. Yeah, there we go. So here are some pictures. So this picture right here from the Chandra X-ray telescope shows the galactic center, which is hard to shoot because it's in Sagittarius. So when you're looking towards Sagittarius, you're looking toward the center of the galaxy, and there's a lot of stuff there because it's in the center. And it's going to be, you're shooting through a lot of star lanes, so to speak. when you're looking out of our galaxy, which is, let's say, towards Cygnus, you're looking at the next spiral arm. It's way more friendlier and stuff. But there's a lot of stuff there that's hard to observe this. But we were able to, we were able to see, we were able to, for a period of time, take a series of pictures and make a video out of this. And so this gives you, this is 10 light days, this little inch here or whatever, this little measurement is 10 light days, so it takes light 10 days to travel this distance, to give you an idea on scale. I think the X is where the black hole is, okay? I'm going to show you a little, we got a thing on YouTube that will show, first I'll show you the real observations, and then I'll show you like a cleaned up simulation of what this looks like. That's this, yeah, that's one. No, it's going to be the other one. So here's I think the out of focus raw footage, so to speak, how they made a video out of it, and you can just see these stars. Like, watch this one just go whip super fast around. You look at this guy, he's way out here, so it just kind of loops over and over again. But they were able to see there's something going on here. It's pulling these stars all over the place, right? But we can't see what the mass is. Now, they can do a lot with this, because if you know, you can figure out the mass of these stars, you can figure out their velocity, you can figure out how massive that black hole is, and they've been able to get a good number on it. So I'm forgetting off the top of my head what it is at this time, but it's huge. So here's what it looks like. This is 17 seconds long, I think. Just shows the star is the black hole, and you can see these stars whipping around it. Look at that one doing that elliptical orbit around it. Pretty neat, right? So this is what we call, I guess this is what we call indirect evidence, right? Because we're not directly observing the black hole. We're observing the effects of the black hole. So we can see these stars whipping around it. It's only something as massive as a black hole could pull the stars this way. There's just really no other answer. Okay, so between that and the X-ray observations, that's pretty solid proof now. There's these things called black holes. So, all right. Okay, so finally, a few years ago, it was probably about 3 years ago, I think, there was a series of telescopes that were able to finally take a picture of a black hole. And so this is actually, it's not one snapshot, it's a whole bunch of telescopes that were used to compile this image, so to speak. So, but there's some other stuff out there that points toward black holes. We got irregular galaxies, or some elliptical galaxies also have very massive jets flying out of them, and that's indicative of a black hole too. So this is M87. This is a galaxy near the Big Dipper. We get to watch this all the time, and it's an active galaxy in the sense that it has this jet of material flying out of this. So this is something you can see in the visible spectrum. So we can see that in our telescopes here. So that's pretty interesting. Okay, so in terms of figuring out that special line, it's called the event horizon, the point at which no light can escape. Okay, Chandra, I'm not going to try to say his name. Chandra was the mathematician that did that. They named a spacecraft. Do we have a picture of Chandra yeah, we do. Chandra over there, the Chandra spacecraft, right? There we go. Okay. And the formula is pretty simple. The radius from the black hole is 2 times big G, which is gravitational constant that Newton first discovered, and then the mass of the black hole divided by the speed of light squared. So anyway, I'm sure it was complicated to derive that formula, but in a science, it's really interesting that a lot of powerful formulas are very basic, like E equals mc squared. It's, once you get down to it, it becomes this beautiful, simple equation that will tell you, if you have this mass, how far away is that event horizon? Now, keep in mind, we're talking about light that doesn't have mass. It doesn't have rest mass, but it has some other type of mass. That's what we're talking about. So there's another radius. If you have mass, if you're in a spaceship, you need to be even further away. So that's like that's for calculating it for light. So a journey to the center of a black hole, what would it be like? According to Einstein, Gravity bends space and time. Once you pass the event horizon, there's no going back. You can't get back. You'll be stretched and stretched. The idea is that your feet are going to be closer, assuming your feet are first, right? They are in cars and the same with spaceships, right? So if your feet are first, it's going to be close to the black hole, so you're going to get stretched. I mean, this is what people think. And then you'll get crunched or something. I don't know. It's not going to. Yeah, it's spedification or whatever. I can't say it. Anyway, so myths, black holes will spit you out on the other side of the universe. I don't know, in the 50s and 60s, they were talking about white holes. Maybe there's places where matter's shooting out of, but we see no evidence of that. I mean, it kind of makes sense because, matter can't be created or destroyed, and it kind of makes sense, that there would be maybe some place where it's, but it doesn't seem that way. So, yeah. Anyway, so we talked about fabric of space, and I said time. We didn't talk about time yet, so let's do that. So if you're in a spaceship that's in orbit around a black hole, your time will actually slow down relative to another spaceship further away. Okay? So they just made up, so 15 seconds will go by or something. And yeah, I'm all right. 15 seconds over here. And so this might be, this would be 50 seconds. So basically, we do know this is true. This has been proven. At least one of the Apollo capsules that went to the moon, that the command module the capsule, they had atomic clocks on it, and they lost a few nanoseconds. So we know that not only gravity, but your speed. This is what Einstein says. Your velocity will affect your frame of reference, how fast time goes. Now, when you're in your frame of reference, like we're all sitting here, we're moving on the Earth, and the sun is moving around the galaxy, we can't feel that motion because it's all constant, right? So we're in what's called an inertial frame of reference. So time goes by normally, right? But if we were looking at someone, or at another frame of reference, if we could magically have a video link, which you can't, but let's say a thought problem, if you could visualize another frame of reference where gravity was stronger or you were going faster, you would see it, people moving slow or fast, depending on which way you're going. So it's been proven. Einstein's theory was proven in the sense that when the astronauts came back, we checked the clocks, and there were a few billionths of a second. We're not talking about much, but it definitely showed up. So any questions from the chat? There is. Okay. You were typing away there, so I thought that was a hint.
All right. So actually, let me go ahead and do this. We'll switch over to the webcam. So that
I think that's my last slide.
It is.
Okay.
It is. All right. Let's switch to the webcam for the live stream.
You want me to turn
and
you want lights?
Webcam. Let's try that. Come on, webcam. All right. Let's do that. And let's turn on some lights so we can actually see.
Okay.
Right. Yeah, we do have a couple of questions.
Okay. Shoot.
From the live stream, and let's see here. Jennifer asks, what determines the stellar nebula's path to either stable or a massive star?
Right. So so basically, what determines what kind of object you get at the end? It's all mass. So it's basically predetermined. You have a stellar nebula that shrinks down to a star. So how big that stellar nebula was, and who knows what causes that, but how much gas and how much matter you have that shrinks into that original star, that beginning mass will determine where it's going to end up. Is it going to end up as a white dwarf or a neutron star or black hole? Depends totally on the beginning mass. Now the only exception that I know of is that if it's in orbit, or if there's another star in orbit, and a lot of stars, are binary and triple systems and even more, it can steal gas from a star and increase its mass. So, but other than that, it's all dependent upon the mass.
All right, another question. Jennifer loved the missing socks scenario.
Okay, good.
I think you got something going there.
Okay, all right.
PJ asks, PJ is 8 years old. He's asking, my question is, are we close to any black holes?
No, we're not. And the one, now you got me. I was just looking at the closest one. It's far away. I want to say it's like 30,000 light years or 20,000. I mean, it's far away. We're not in any danger of getting sucked into a black hole. They're pretty far away.
All right.
The more scarier thing than a black hole actually is supernovas. So when the supernovas go off, they would wipe out life nearby those stars. And again, we're not near anything that looks like it's going to go off anytime soon.
All right. Cindy asks, can you explain what causes the jets coming out of a black hole when nothing, even light, can escape?
Yeah, okay, because it didn't get into the black hole. So what's going on is that material is making its way, swirling around like a whirlpool, and getting as it's about to get sucked into the black hole. And there's some dynamics going on with the black hole that creates a strong magnetic field, and that stuff gets shot up into those magnetic field lines and gets shot away from the black hole. So I don't know how much of the stuff makes it in there versus how much gets turned into X-rays. I don't know, but that's what's going on. So that stuff hasn't gone into the black hole yet. It hasn't crossed that event horizon.
All right. That's the questions we've got right now from the live chat. Are there any questions here?
Those are good. Those are good questions. I was getting nervous. That was good.
All right. If you have a question, we bring the camera over here. The camera, the microphone.
Do the black holes eventually stop sucking stuff in?
Yeah. Okay. Yeah. Okay. So now it's really getting out of my field. So what happens eventually is that as the universe expands, what we think is going to happen is that they eventually evaporate. Black holes, there's something called Hawking radiation they are giving off, and it has to do with something called virtual particles and all this. It's very complex. But basically what's going to happen is as the universe expands, we're actually accelerating, which is a surprise that we found in the last 25 years or so. So everything's moving further and further apart, and it's getting faster. So at about the age of about 1 Google, which is 10 to the 100th power years, the only thing that's going to be left in the universe will be black holes, because everything's just going to, because not only it's the fabric that's stretching. It's not just that we're getting further apart. Space is getting stretched, okay, and eventually atoms won't work, and it's going to, it's getting pretty depressing, right? So nothing's going to work. It's going to be, so anyway, that's when the evaporation of the black holes occur. So it's 10 to the 100th number of years. That's what the Google is. So Roger Penrose, who has this theory about the cyclical universe, he's saying that, you could do a whole program on this, and I haven't read up on it lately, so I'm a little rusty. But his idea is that when we get to that point, time is basically going to be non-existent, and that he thinks that another universe will appear, because it's going to be very similar conditions to what is in the beginning of what we think is the Big Bang. So it's really, he thinks it happens over and over again. So.
All right, any other questions? Oh, Ben, one of our interns.
Okay.
All right.
How exactly are black holes related to dark energy and dark matter?
Oh, jeez.
Okay, that's how.
That's it. Well, okay. So the idea, dark energy, I don't know that much about. Dark matter is the idea. What we believe, and it has to do with that acceleration, is that there's dark energy pushing the universe, accelerating the universe. I don't think there's any relation to dark energy, but they make a part of the dark mass. So there's this missing mass. So just let me back up for those who don't know this. When you look out into the night sky, you see all the stars and you see all the galaxies. You think that's all there is. No, that's only like 4%. They think by mass, what we visually see is 4%. So 96% is this dark matter, okay? And it's the dark energy that's accelerating us. So, I think the black holes are part of the dark matter, I think. So then they're trying to figure out what's making that dark matter. Is it something exotic, or is it something ordinary? They haven't really figured that problem out. So.
All right. Any other questions? All right. I think I'm guessing our skies are not as they should be.
It's clear. No. Did you check? Just check, just in case. So that happens all the time. Like you get a cold front or something, and it can just totally clear. Or as soon as you guys leave, it'll clear. Yeah, it'll clear.
As soon as you get back onto 26, right. It'll just really be nice. So.
Oh, it's still snowing.
All right.
Okay.
So,
all right.
So for those of you who did actually pay to come in tonight, if you go back to the cash register, we'll give you a card to come back on another night for free.
Yeah.
So the rule here is you can't leave Kopernik until you look through a telescope.
Right.
So we may have to push that off until the next time. But again, we've got another 3 weekends, another 3 Fridays plus our Holiday Horizon event on the Saturday the 18th. So you got at least four times. In January, we'll do one evening for a program. In February, we always do a thing called the Winter Star Party. And Kopernik was actually born on February 19th, 1473. And our Winter Star Party will be on February 19th, 2022. And we're still working on who's going to be our speaker, but we always have cupcakes. We have to celebrate. We have to sing Happy Birthday to Kopernik. And then we'll start up again our Friday night programs in March. Again, if there is a stellar something of note, like I heard there's a comet Leonard. I think is that may right now be coming up in the morning, but we'll keep an eye on that. We have done some live streams of various astronomical events.
Lunar eclipse.
What?
The lunar eclipse the other day.
Yeah, we just did. We did the lunar eclipse. Right. Right. So we'll start seeing it as it starts approaching the sun. It'll be more of a early morning object, but then once it gets beyond the sun, hopefully if it hasn't completely melted, we should be able to see it in the evening. And like last not this, it was the summer of 2020. It was the comet Neowise. Did anybody see that? It was, and we actually did a couple of live streams about that. So anyway, if for those that actually are watching on the live stream, also if you're in a position to help us, there's a little link down below to help us. If you can donate toward that to help us support us in our live stream. And if you're not already a subscriber, please go to our website. There's a link to show you how to become a YouTube subscriber. And if you can't make it up here on a Friday night, you can watch it live on the live stream. Or if you got something else going on Friday, any of our live streams are permanently saved on our YouTube channel, so you can always go back to it. So if you want to go back to this.
Yeah, and people online, if you could make that thumb blue, give us a thumbs up if you like the program or whatever. So there's such a delay when I stood up to look at it. It freaked me out. There's a delay.
Oh yeah. It's about a 20-second delay.
So I will I meet you all, particularly the kids and maybe the adults young at heart. I'll show you this on the big one, the big spandex universe. We got our marbles ready, Ben? We're good? Okay, I got the big one. So, all right. Well, thanks a lot for coming, everybody.
Thank you much.